Here we are. Right, double junction, high transmission coefficients made from yes.
Question. Why should the integral under the distribution not be 1?
This is a property of distribution. It's,
Okay. So it's not a probability distribution. It's not a chance for a given transmission.
right, so the integral, in principle, will give you average number of transport channels.
So the average number is infinite.
Yes, that's a trick. We have mentioned it already in lecture number 1. You can always think of a structure as a constriction, something small, which is connected to gigantic links. And the resilience of transport channels come into another structure. But most of them just don't transmit, have very small transmission coefficients. So there's no wonder then, for instance, this integral over transmission distribution just diverges like it does here.
So we have to calculate the integral of t over.
Yeah, if one, for instance, one computes conductance, one integrates t, this is distribution coefficient, and this is always fine.
Yeah.
Thank you. This is a good question. So this is possibility to have high transmission coefficients, and that has everything to do with this formula, with 2 barriers and phase factor in between. Good. That's what we got. Let us talk. That's basically, I have said everything about this. Let us talk about different example. Let me talk about chaos. Chaos, it's interesting. I'm chaotic. You might be chaotic as well. It's interesting to quantify this. See, I have to pin this window. Let us consider kind of a billiard for electrons. Let us take gate and define some potential walls for electrons of this shape. And let us just treat electrons as particles. Chaos is manifested at classical level, quantum level, it's basically the same. So we can understand what's going on at classical picture. So the statement is that the electron motion in such a setup is chaotic. What does this mean? Let's talk first about a single electron. This single electron, single trajectory, enters this cavity. It is reflected from walls several times, and already after second or third reflection, there are several reflections, it already forgets whether he came from left or right side. Like you would do if you enter a maze. After several turns, you forget which side you come from. That's one definition of chaos. Another definition, let's have 2 electrons which enter this billiard with two trajectories which are very similar. They have almost the same incident angle and in the same point. Chaos means that these two trajectories diverge. The distance between these two electrons, which initially were close to each other, will increase, and the difference kind of roughly doubles at each reflection. Right? It means that I would try to plot, for instance, which side the electron would go versus the incident angle. I will have very funny function which is not continuous at all. It will have, like you have heard about fractals, very peculiar fractal structure manifest in the chaos. Good, that were complex things about chaos. We can treat it simply with our method. How we can do this? Let us realize that this ballistic transmission through the constrictions can be modeled with something which we know is a ballistic conductor. So to describe this chaotic cavity, it's a model of chaotic cavity. We just need to combine two ballistic contacts in series. Here I did it, a little bit of algebra. There is again I-phi characteristics of one connector, second connector. Good, there's some tricky equation to solve, kind of perhaps like equations you've been tortured at school with sine, cosine, but not that complex. It is still a school problem and I can get an answer. Do it in Playback formula and this is the answer. Analytical answer. Again, there's a parameter which depends on asymmetry of two junctions only. And it is zero when the situation is symmetric. Okay, again, it's a simple function, but to get a good vision on that, let us plot it. We plot it. And here's the result. First of all, symmetric. Yes. Did this curve. Similar to diffusive contact, it will diverge both at 0 and unity transmission. Interesting thing happen when these two ballistic junctions are not the same, right? Then there is gaps at the same, which means that the North transmission coefficients with low values. The distribution just starts with some critical coefficient. For instance, this one. And diverges upon approaching unity. Okay, that's a little bit natural. So, suppose one of the contacts is the smallest. Then in good approximation, we can disregard another contact. Right? because it has big conductance. It's like in circuits we disregard elements which have big conductance. They kind of can be regarded as short circuits. Fine. So we have this small one and big one. So if we disregard it, if we short circuit, then all transmission coefficients will come to 1. If it is finite, they kind of depart from 1, making some distribution around 1. Good. This is what we can tell about chaotic cavity. Let me now switch to something completely different. Let me talk about spin transfer. Again, because it's a simpler topic, but it has some applications and some interesting unusual physics to talk about. First of all, let's have some source of spin, or we can make a source of spin. This is tricky unless we use some natural phenomenon. And this natural phenomenon is ferromagnet. We know that in some materials, some of these materials are metals, electron spins are aligned. So that gives the difference in numbers and in velocities in all properties for 2 directions of space. Here I sketched what has happened. So for non-magnetic metal, we would have this parabolic dispersion law, and all states would have been filled up to this energy. Then the parabola is split into 2 pieces. Electrons which spin up have larger energy, and electrons which spin down have smaller energy. This is characterized by internal energy exchange field, which is proportional to the magnetization. Right, and you see what has happened. This those different numbers of spins. So now we have more spins down than spins up. Fine, this is a simple magnet of a simple model of ferromagnet. And as I told, basic problem of spin transport is to consider the systems which contain normal metals, non-ferromagnetic metals, and magnetic ones. Right, let me first talk about this problem in terms of template. What do I have to fill? Which matrix voltages and matrix currents should I use? First of all, matrix voltage. It has spin index now. What does it mean? That just means this, right? So in addition to common voltage, we will have different chemical potentials for 2 different spins. This difference is felt in the direction of magnetization, so it is a vector. So we have a combined matrix voltage, which is related to chemical potential and to spin accumulated in the lead. Right, matrix current that we have already discussed in the last lecture. It has electric part, electric current, and it has flows related to spin, to all three components of spin. That's why spin current is in principle three component quantity. Right. What I want to stress, first there is a simplification. In the series, if one uses these matrix voltages, one ends up with linear relations between matrix voltages and matrix currents. But there is also a complication we have not considered so far. The spin conservation is approximate. There are big interactions like spin orbit interaction, which lead to spin relaxation. Spin electron forgets its spin. It happens at a rather large scale, so that sometimes it can be disregarded, but there are all these processes like this. So it would be also good to take some care about these processes. Good. There are very many divisions or borders which you can draw between classical physics and quantum physics. Strangely enough, in the stuff I will tell you about, the difference is the border is unbelievably simple. If we talk about the structures where ferromagnetic leads have collinear magnetization, either parallel or anti-parallel, it is classical transport. If they are at some finite angle, the transport becomes quantum. Good. Let me talk about collinear transport first. Let me have a system to describe. I would like to have two leads with parallel magnetizations or antiparallel, and I would like to have a normal metal, normal node between these two leads. Sure, what is the simplification here? We can just regard it as a situation of two voltages. Two voltages which, did I lose the connection again? Strange. Okay, whatever. Two voltages for two different voltages for different directions of spin. Right? So at this situation, we can consider electrons as two with different spin as completely different particles, completely different species. Number of each particles is conserved, and since species are different, the conductances which they feel are also different. Good. Then we just write that there are two components of spin current, two spin currents corresponding to spin up and spin down, and right, just find their balance. Yeah. So there are many strange ray codes in this spin business, which is commonly called spintronics. Like electronics, it's about electrons, and spintronics is about spin. Right. I would never give a Nobel Prize for such a simple drawing, but people do. What that simple stuff with some decorations have actually resulted in a Nobel Prize. Let me tell you how what is all about. Right. We have two spin directions, two contributions to the current from two different spins. And let me regard these two as two parallel circuits. Upper branch and lower branch for two different spins. Good, and let us figure out the difference between parallel and anti-parallel configurations of the leads. We have two resistances, one for spin up, say minority, and spin down, which is majority. So these resistances are different. Fine, so let us take these resistances, big and small, and let us combine that for parallel configuration. In this case, minority spins, they remain minorities. In all the circuit, majority spins remain majorities. So these resistances are the same on both ferromagnetic interfaces. All right, we can do algebra, we can find the total resistance. Let us now consider anti-parallel configuration. Then you see that resistances have changed. And in fact, in both branches, for spin up, for spin down, we find small and big resistance. Because spin that was minority in left lead belongs to majority in the right lead, and vice versa. Fine. So we have to deal with a circuit like this. Anti-parallel configuration gives a bit different value of resistance. Why is it so fascinating from the point of view of practical applications? Because you have a way to detect whether two ferromagnets are parallel or anti-parallel with electric current. You just apply voltage, you measure current, and you know how whether they're parallel or anti-parallel. And this is a way to read magnetic memories. So since that, spintronics is used in magnetic disk drives, stuff like this. Good, and because of appreciation in applications, that stuff. These few decorations have been given Nobel Prize. What were decorations? I put here some resistor in dashed line. Dashed means that it doesn't, it is not present in approximation, could be put to infinity, as I put it on the sheet. Can you now figure out what will it describe? Just of all, what does it connect? It connects spin up branch with spin down branch. So electrons with spin up would have to go through this resistance and become electrons with spin, with opposite spin. The same for opposite flow. So in fact, this resistor describes relaxation, describes the processes by which spin is flipped. Fine, that was a spin valve. Let me talk now about non-collinear magnets. And as I said, it looks like it must be the same situation. It's just some marginal angle between these magnetizations. However, it immediately brings quantum mechanics. Of course, it is a quantum mechanics which is very much hidden in this conservation laws, but still quantum. To understand this, let us recall that if you rotate spin, for instance, if I consider a spin in x direction, it is a quantum superposition of two states, spin up and spin down. So any deviation from quantization axis will result in quantum superpositions. That's why it's quantum physics indeed. What does it mean in our approach? It means that we cannot really consider two independent currents for two spin directions. We also have to take into account the superpositions non-diagonal matrix elements, corresponding, for instance, to the current in x direction. Good. So now we need to have some balance equations and equations for currents in this situation for non-collinear magnetization. All right. So the system is the same. Now I'm trying to concentrate on a single junction. And I don't know where the quantization axis is. What can I do? I can assume that there is some related to ferromagnet. I will turn my coordinate system in spin space in direction of this axis, and I will analyze the situation because it should be simpler in this convenient reference frame. Fine. What will I find in this system, in this system of coordinates, in this reference frame? First of all, there will be the same effect which I have already described. There will be currents of electrons with different spin directions. But it's not everything. There are also currents in the direction of in perpendicular directions. They should be proportional to voltage differences in perpendicular directions, in directions x and y. We see some voltages, as are not voltage differences. Why is it so? Because voltages in this direction are zero in the ferromagnets. The reason for that histories of electrons with different spins are so different that all quantum superpositions are destroyed in ferromagnets. Right? That's why we need we only need to know voltage in the metal node. Good. And there are two values, current in two components of current, two components of voltage, and the relation between this, it's like it is written like this. It contains two real coefficients, which can be seen as a real and complex part of some complex, real and imaginary part of some complex number. This complex number is happen to be named mixing conductance. Why it is mixing conductors? Because it describes processes whereby spin changes. That's why it has plus minus indices. What is why it is conductance? Why it is natural to call it conductors? If I take scattering matrix and express this mixing conductance with scattering matrix, let's see what I have. I have reflection coefficients of spin up and reflection amplitude for spin up and reflection amplitude for spin down. If these spins are the same, I would have reflection coefficient. Reflection 1 minus reflection coefficient is transmission coefficient. So I'm back to conductance. But it's not quite conductance, it says proportionality coefficients between spin currents in the direction perpendicular to spin quantization axis to magnetization of a given magnet. Good. So for a single junction, the relation between current and voltage has two parts. One is somehow trivial, intuitive, it's spin both. Another one is mixing conductance. Good. Now we need some algebraic or geometric exercise, I'm afraid. What's the matter? It is easy to write down these relations in the basis corresponding to quantization axis. But these bases are different for two junctions, so we cannot combine it simply. To that end, we need to rely this relation in arbitrary reference frame in spin space. So how we set this reference, the spin space? We need to perform rotations in spin space. This rotation just takes the axis and put that axis in the direction of magnetization, this vector M. Fine? And we need to apply these rotations to each junction. Let me look at this. So that was in a certain coordinate system. Magnetization axis in the direction of Z. Now I would like to rewrite it in a different coordinate system. In order to do this, I need to perform rotations of all wave functions in spin space. So two spin indices, so I need to rotate both. That's what I do. It becomes Klasmy, but again, it just Pauli matrices expressed in the components of magnetization vector. All right, let me perhaps get to concrete problem to describe an example of non-collinear spin wave. So it would be a classical spin wave if magnetization has a parallel or antiparallel. I just want to consider it as an arbitrary angle setup between the directions of magnetizations. Right. I will take identical junctions. I will take antisymmetric bias between the leads. Very well. Then the question is, what would be a good coordinate system to work in? You still used to have to choose some coordinate system in spin space. Right, got to think a little bit geometrically. So we have one magnetization vector, another one, those angles theta. How would you choose coordinates? These vectors, magnetizations, they have the same modulus. And in this case, it is natural to take sum and difference of these vectors. So let that axis to be in this direction, right in between the vectors, and x-axis just perpendicular to it. Does it make sense to you? Fine. Then I just write the components, and you understand now why those theta divided by 2. Right, with this, I can write these matrices, use, and implement those. Fine. Now I need to invoke again balance of spin currents, Kirchhoff rules that we discussed. I write spin currents in one junction, write spin currents in another junction. right? Understand that they are adjusted to different magnetization axes. So I need to use different matrices U for these currents. And I can make an equation equating these currents, spin conservation. Right. Let me just show you the answer. The answer is like this. We can find a formula which approximates, which kind of connects two limits, parallel and anti-parallel. What are parameters in this formula? It contains polarization, it contains the same factor which describes spin valve. This is a ratio between conductances with of minority and majority spins that we have. We also have a parameter which contains mixing conductance. And this gives these expressions of conductance upon the angle that do depend on both parameters and provide us with a quantum mechanical expression which connect these two classical limits. Fine, so that was an example of quantum circuit theory. That's conservation of spin currents, which has many technological applications nowadays. It was about spin electronics. Good. Any questions? Next time we'll have yet another change of topics. Perhaps it's a good time to upload some homework for your son. As I said, I don't check your homework, you don't submit it, I don't check, it's mutual. But at some stage, I don't remember what date is this. At some stage, I will tell you something about solutions of the homework. Fine, thank you for your attention. See you next time. So thank you, Zoom participants. I will finish this meeting.